And I do want to mention that you need to keep the homework coming. You know, this is something that you know about math classes. We learn our information in chunks, so we learn enough information in one day to do an assignment, and then we build on it in the next day. So if you're falling behind in assignments, try to take care of that right away. Remember, you have kind of an extended, weekend this next weekend to play catch up on things. But don't let things go too long, because our brain is going to start to say, hey, that was short-term memory, and I need that space for other things. And so it starts to kick out the short-term memory. And it's when we do the homework that we lock the things from our short-term memory into our hippocampus, our long-term memory, and then it'll stay there. And that's what we're looking for. So homework each day. Great idea to do that. Alrighty, in section 4.2, we're not going to have the whole time together today, which is kind of nice for us once in a while, because we've already talked about our two famous triangles, and we're down here to evaluate trigonometric functions with a calculator and apply right triangle trigonometry to solve right triangles. And a lot of that is something you saw in geometry, so hopefully it'll feel like much review as we go through that. All right, so here we are where we get to the point where we have to remember how the calculator works for everything that we need. And the dangers of evaluating trigonometric functions with a calculator. Number one, we've forgotten what all the buttons are for, and it's just plain old operator error. Number two, using the wrong mode. That's going to be important for us. When you were in geometry, they typically just use degrees. You set your calculator in degree mode and you left it there. But now if we have something that's in radians, which of course we know is pi involved, or it does not have that little degree symbol for a label. So watch for that degree symbol. Use degree mode on your calculator and radians mode for anything that's pi. So before I get into what we're seeing there in the packet, mode is right up here next to the blue second button. And when your calculators come out of the factory, they are always set to radians mode because that's more exact. When you need degrees, you'll have to use your arrows to go down to radians and then to the right once, 2 degrees, and then hit enter. And now it's going to do whatever it is you punch in degrees. It does not reset every time you do a problem. It will be in degrees until you change it to something else, so that's important. I also want to remind you that our calculator only has sine, cosine, and tangent buttons. It doesn't have cosecant, secant, and cotangent. But what we can do is we can find the sine and then take its reciprocal. We can find the cosine and take its reciprocal, the tangent and take its reciprocal for those secondary trig functions. So if you want to know a cosecant, you'll have to evaluate what the sine is. Let's say it's 13 degrees. And then to flip it, you can either take 1 and divide it by the answer, or, let me try it again, a different way. You can use this little x to the -1 button that's just to the left of the sine key, because what that does is it takes the reciprocal. It raises it to the -1 power, which of course is the reciprocal. So you'll get the exact same answer. So you have to remember what those buttons are for. And up above sine, cosine, and tangent, you see sine -1, cosine -1, and tangent -1. That is not for cosecant, secant, and cotangent. Those are inverse buttons. What those do are if we tell it 4.445 blah, 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 and we want to know what was the angle that gave us that, we use that inverse function to work backwards and get the angles. So know that we don't have our secondary trig functions on here, but we have a way that we can get them. So when we look at what was punched in down here, hopefully we'll be able to see the errors. So this one says evaluate the sine of 10 degrees. And you punch it in and you get -0.544 blah, blah, blah. We should know that's wrong. We should know that, hey, that must be in radian mode, because that is not what you should get. And that's because it came out to be negative. And when we draw 10 degrees, it is definitely in the first quadrant. And in the first quadrant, sine, cosine, and tangent are all going to be positive. So this should be a clue. Uh-oh, I forgot to change it into degree mode. It's in radians. Then, like I said, those inverse trig keys, and they want to know which is correct. We're supposed to evaluate the cotangent of 30 degrees. Well, on our calculator, we'd have to tell it, find the tangent, and then we'd have to find its reciprocal. So, innermost parentheses here, we are definitely finding the tangent of 30 degrees, and then we're taking its reciprocal by raising it to the -1 power. So this is right. Over here, this is going to tell us the angle that would give us 30 as the ratio of two sides. So this is the wrong button because they use the second function to get that. Other things where we have to know the calculator's limitations, and that's using function shorthand that the calculator does not recognize. So this error, like it says, it's less dangerous because it usually results in an error message when you make a mistake. We'll often abbreviate powers of trig functions, writing, for example, sine cubed theta minus cosine cubed theta, when that's not the way the calculator would take it. The calculator would need find the sine of theta, cube it, minus find the cosine of theta, and cube it. So the calculator doesn't recognize our shorthand notation, and it's going to tell us that there's an error in there. Because one of the most famous trig identities that we're going to use a lot is sine squared theta plus cosine squared theta equals 1. And if you look at that, you realize, well, technically that's not right, because we should have parentheses around the sine of theta and square it, plus parentheses around the cosine of theta and square it equals 1. But this is the shorthand way that it's written. So calculator doesn't know shorthand. We have to interpret it for it. Now, another mistake, not closing off parentheses. You know, you kind of have to watch your screen as you're punching it in to see, what do I get parentheses for and what don't I? So the sine of 30 degrees, finished off with parentheses. Cool, there it is, 1/2, 0.5. But this next one, the sine of 30 plus 2. The calculator is going to try to figure that out as the sine of 32 degrees because it's waiting for you to put another set of parentheses on there. And if you don't put it on, it assumes that it's at the end of what you've typed in. But the bottom one would actually give us the sine of 30 degrees, calculate it, stop at 1/2, and then add 2. So again, you have to watch for parentheses. You know, when do they pop up and how do I need to finish those off? So those are the ways that we can use our graphing calculator to help us find some of the trig functions. Remembering, of course, that we shouldn't be grabbing a calculator for any of the special angles, which are our 30, 60, 90s, our 45, 45, 90s, and as we get into it, the quadrantal angles as well. It is usually impossible to find an exact answer on a calculator when evaluating trigonometric functions. I'm going to give you a for instance. Sine of 60 degrees, that's an important one. We, of course, found that to be the square root of 3 over 2. But I check my mode, I'm in degrees, and I want the sine of 60 degrees. Finish off my parentheses. That doesn't look anything like the square root of 3 over 2. Now, if you see it often enough, you start to recognize it as, oh, that's the decimal equivalent for the square root of 3 over 2. But what we want to do is make sure that if we are supposed to find something that's perfect and nice, that we do that. If it's a word problem, yeah, we're going to have to grab a calculator because they want to know an answer in the end. So this says, show why the following trigonometric identities are true. And this is going to start us down the road of being able to prove things algebraically using trig. So this says the cosecant is 1 over the sine of theta. Well, to figure this out, I want to go back to those definitions of opposite, adjacent, and hypotenuse. So this would be 1 over, and then I remember SOHCAHTOA, sine is opposite over hypotenuse. And then you realize, well, we don't divide fractions, we multiply by the reciprocal. So I'm going to change that 1 into 1 over 1, because when you work with fractions, it's always easier to have everything fractions. And multiply that by hypotenuse over opposite. Which is, of course, hypotenuse over opposite, which is a secondary trig function, cosecant. So we just did a little algebraic proof here of why 1 over the sine of theta is truly cosecant. The second one we saw yesterday, but remember I told you this is really, really important. This is one we have to know, and so we need to see it a few times to make sure everybody remembers. The tangent of theta is really sine of theta divided by cosine of theta. Again, use those definitions, opposite over hypotenuse and adjacent over hypotenuse. Think about how fractions work. Multiply by the reciprocal. And then see that your little hypotenuse on the top and the bottom are going to cancel out. And then think, well, which of the trig functions has that for a definition? Opposite over adjacent is tangent. So yes, really, really important one there to remember. Oftentimes when students are having trouble getting their trig identities to work, one of the things that we'll say for a fail-safe is try to get your proof in terms of sine and cosine. Try to just work with those two primary trig functions, and maybe you'll get it. Number 3, this is a little bit more, and this is, like I said, it's the most famous of the trig identities. Sine squared theta plus cosine squared theta equals 1. So we want to know, how did that come to be? And we use the definitions. So we start there. Opposite over hypotenuse squared plus adjacent over hypotenuse squared, and we want to see what that equals. Well, we could distribute that squared because remember, whenever you have pure multiplication or division inside parentheses, then you can distribute those powers. Well, it's fractions, and with fractions, you want a common denominator, which we have. So this will be opposite squared plus adjacent squared over hypotenuse squared. And then we have to think about this for a second. This is right triangle trig. Opposite squared plus adjacent squared. This is a squared plus b squared. That equals c squared. That's the hypotenuse squared. So this equals hypotenuse squared over hypotenuse squared, which is, of course, 1. So you have to make that connection to, okay, let's go back to the triangle. Let me see that visual of opposite and adjacent. Oh, that's a and b. So a squared plus b squared equals c squared. And that gives us 1. So like I said, kind of a beginning of little algebraic proofs for trigonometry. Now, a triangle has 6 parts. When we find all 3 sides and all 3 angles, we are said to be solving the right triangle. So with these problems, you're going to get most of the time a picture or a description of some of the sides and the angles in your triangle, and they're just going to say solve. And solve means we're supposed to know, find anything that's missing. Anything that's not clearly labeled. So example 5 says we're going to solve a right triangle. Have a little picture for us here. A right triangle with a hypotenuse of 8 includes a 37-degree angle, which we can see down here in the lower left corner. Find the measures of the other two angles and the lengths of the other two sides. Now, if we're hoping for some labels here, the only ones they gave us were the lowercase a and b. But that's supposed to be enough, because in geometry, we were supposed to learn that if this is a lowercase a, the angle that's opposite that is an uppercase A. And if this is a lowercase b, that's an uppercase B opposite that angle. And just for simplicity, I'm sure we'd just call that one C. So we'd have A, B, and C. Now, they told us about the 8. They told us about the 37. We can see the little square drawn there and say, oh, measure of angle C is 90 degrees. And then we remember that every triangle has 180 degrees in it. So 90 of it is already gone for angle C. That means we have 90 degrees remaining for the other two angles. And we'll have to figure out what 90 degrees minus 37 degrees is, and then we'll have it. So we have 53 degrees. Measure of angle B, 53 degrees. Now, the ones that are going to take a little bit more work. That's going to be A and B. So what I want to do is clearly label what I already know. And what I already know is that A, measure of angle A, was 37 degrees. I know that little a would be opposite to that angle. And I know that 8 would be the hypotenuse. So opposite over hypotenuse, I remember SOHCAHTOA, that's sine. So the sine of 37 degrees equals little a over 8. So if I want to figure out what little a is, I'm going to have to multiply both sides by 8. Now, I'm going to go ahead and wait on that so we can punch both of those in at one time, because we have another side to find. And every once in a while, somebody wants to put that 8 sine of 37 that we get for a decimal over here, and then use that to try to figure out what b is, and with the Pythagorean theorem or whatever it may be. We shouldn't be doing that, because remember, we're trying to find elegant and perfect answers. Chances are pretty good we're going to have to round 8 sine of 37 degrees. And it's possible that we goofed up when we said the measure of angle B is 53 degrees. So if we use something that's been rounded, or we already might have made a mistake on, then we're increasing our chances of getting another part of this triangle wrong. So instead, it's better to go back to the beginning and say B is adjacent. I absolutely know the hypotenuse is 8. I absolutely know the measure of angle A is 37 degrees. So I should use adjacent over hypotenuse to find that one, which is cosine. So cosine of 37 degrees equals b over 8. Multiply both sides by 8. All right, now we can punch these in and round them to 3 decimal places. So we had 8 sine of 37 degrees. .815, rounding to 3 decimal places. 8 cosine 37 degrees. 6.389 to 3 decimal places. So let me get that written down. And now the last thing to do would be to look around for labels, you know, because we've got the label for degrees for our angles, but maybe something up there said inches, meters, something. And we realize we got nothing. So a good old U for units usually works. But we don't take off points if you don't put the U for units. If in fact they did give you a label, then yes, we'd have to take something off if you didn't label it correctly. But for units, normally we just put the numerical value down and we have it. So again, the key here is trying not to use something that you found and may have made a mistake. Go back to the original because it'll increase your chances that you'd actually get one of them right, even if you made a mistake on the other one. Alrighty. Now, here comes our applications objective. Real-world applications involving direct measurement are frequent. We need to be able to find distances that we would rather not measure directly. Somebody thinks the water tower looks like it's starting to sink a little bit into the ground. I'm wondering, did it lose any of its height? Well, they can find somebody else to carry the measuring tape up there. I don't want to do that. So what they would use is indirect measurement. And this says we're finding the height of a building from a point 340 feet away from the base of the Peachtree Center Plaza in Atlanta. The angle of elevation to the top of the building, so here's you're looking down, you're down here and you're looking up 65 degrees. Find the height of the building. So we look at this and we try to figure out in terms of definitions which trig function we should use. And the height is opposite. Oh, I don't know if you can see that well enough. Let me put that over here. H is opposite our 65-degree angle, and the 340 is right next to it, which would make it adjacent. And you think, SOHCAHTOA, oh, opposite over adjacent, that's tangent. So tangent of 65 degrees equals H over 340. And obviously we'd have to multiply both sides by 340. And we'd make sure our calculator's in degree mode, which, you know, doesn't hurt to every time you have to do one of these switch it, but we know we've been working in degrees for a while here. And I need to know what 340 tangent of 65 degrees is. Oops, wrong one. There it is, 729.132. And in this one, because it was an application problem, there should be labels up there, and we see that distances are given in feet. Now, if we wanted to be more exact, you know, this one, that's probably exact enough, but we certainly could go with feet and inches. So we could do 729 feet, and then we'd want that decimal portion to figure out the inches. So I'm going to subtract the 729. Now I have just the decimal portion, and I know that there are 12 inches in a foot, so I'm going to take that times 12. So not quite 2 inches, but with rounding, that would be a little more exact than just saying 729.132 feet. So there we are. And like I said, should have had a feeling like, gosh, deja vu, I think I've done this before, because in geometry, you were doing this kind of right triangle trig. And like I said, that's it for today, and I'm not going to move forward into the next section because, doggone it, I think we deserve a little break here. You guys have been working really hard. And there is day 2. Hopefully we cleared up, you know, anything that you needed from 4.2 day 1, but I'm here, so if you have questions on some of the homework that you've already been doing, feel free to hang on and ask about those. Or, you know, you could pop off and start working on the homework and just pop back on. I'll have it open until 8:55 for anybody that has any questions. So to those of you that are going to leave, have a fantastic day.